Yeah. With this, let's move on to the our the next session. Uh, it's going to be an interesting one. Bhavana from and also she was a former employee of IBM. She's going to be sharing some of her experience in quantum journey, and definitely this experience is going to be helping lots of beginners who can get started with the quantum with the hardware, whatever you learned from Chris, and now you can apply that to start as a journey, as a Q journey or something like that we can create. Bhavana has got 7 years of experience and working with IBM for many years on the performance modeling and the CPU related optimization. Worked with the open power a lot, and she is now currently working with ARM for the similar the activities for the ARM the CPU core. With this, I'd like to invite Bhavana to start a presentation.
Thank you, Ganeshan. I hope I'm audible.
Yes, Bhavana.
Okay, yeah. Okay, so thank you, Ganeshan, for providing me with this wonderful opportunity to share my experiences with you all. And it's really exhilarating to see so much of interest and traction for this field of quantum computing. So, okay, with this, let me just share my screen. Okay. Hello everyone. Um, I'm here to basically share my experiences with the quantum summer school that I attended recently, and also to share my opinions and views on what quantum computing is and what is it that I like about it. So it's not going to be a deeply technical presentation as such. So most of the numerical stuff with formulas and stuff would be taught to you, I'm sure, in the next few sessions over the next 2 3 days. This is just a joke that I found sometime back on quantum computing. I'm not sure how many of you would be able to understand this, but I'm sure towards the end of this presentation, you would be able to get it. Okay, so with this, let's just jump right in. So why quantum computing? So why is this world so crazy about quantum computing, especially in the recent times? So this is the type of scaling that we get to see when we compare classical and quantum computing. So there are a lot of problems which are short running and end up taking the same time on both classical and quantum computing. And yet there are several problems which are really hard and take almost thousands and thousands of years to run on a classical computer, while a quantum computer would be able to run that for you in just a few minutes or even a few seconds. To give you the context, let me give you an example. Let's say you want to form a long string filled with complete random numbers, and you want to test if this string is random or not a million times. So to do that on a classical computer, it would literally take you around 10,000 years to finish, while a quantum computer will just take 200 seconds to finish. So that's what we're talking about. And another good example, I think, would be the IBM's Deep Blue quantum computer, which was being created sometime in the late 90s. And in 1997, it in fact managed to defeat the world's chess champion in a chess championship. How was it able to do that? It was able to find the best possible move out of a 200 million set of possible moves. Now, can you imagine it? I mean, even with our human thinking, you would not be able to process all the 200 million possible moves in your mind and then process them so quickly that you would be able to play next and win the game. So that's what we're talking about here. The kind of speed improvement gain that we get with quantum computing is enormous. We're not talking about 1x, 2x, or 10x, but it's for in some certain applications, it's literally a million X improvement with quantum computing. So we'll talk about what kind of applications are good and work well with quantum computing and which ones are still better with classical computing. So I just want to touch upon a few other interesting applications on quantum computing. And it was nice to see so many people being interested to first know what are the applications of quantum computing in the chat as well. And Dr. Chris touched upon a few of the trending applications, especially in the field of ML, AI, deep learning, CNN, image recognition, and also in chemistry, which is my next application. So in chemistry, basically, the problem is to accurately model the complex structure of chemical compounds, chemical molecules like amino acids or proteins and like peptides, like Dr. Chris has mentioned. And right now, because of the limited computing power that we have to resort to certain approximation techniques like Markov models, the hidden Markov models, because of which we are not able to really get the accurate picture of the molecular structure. Now, why do we need the picture? Because we would be able to then predict what would happen when this molecule goes through certain chemical reactions. Now, take, for example, the nitrogenase enzyme. So the good bacteria in the soil basically fixes the atmospheric nitrogen and converts it to useful ammonia, which is useful for the plant growth. And it does this using the enzyme called nitrogenase. Now, if we know the exact accurate molecular structure of the nitrogenase enzyme, it would be very easy for us to understand how this entire chemical process really takes place. And we would be able to then create our own energy efficient fertilizers for plants, because the current fertilizers that we have do not do as well as this bacteria does in converting nitrogen to useful ammonia. So there are a lot of other applications basically to understand the complex structures of molecules and be able to predict what would happen when they go through chemical reactions. Another interesting and favorite application of mine would be the DNA sequencing. So let me take the example of COVID-19, for example. COVID-19 and other, any disease basically ends up mutating your DNA and inserts different proteins and amino acids in certain locations of your DNA. So in order, if there's a new pandemic or a new virus or something, that new disease that comes up in the world, the researchers, what do they basically do is first try to identify the mutation sites in the DNA, find out which amino acids have been converted, which proteins have been converted to what, and then that would enable them to find the right drugs to fix the problem. So in order to do that, they have to extract the DNA of the patient and match it up with the reference human genome. And a human genome has these 4 strings, A, T, G, C, D amino acids. And it's basically a very, very long string of ATCGs, which are called the bases. And it probably contains around 1 trillion of those bases. It's that long. And you basically have to do some sort of string matching to get the patient's DNA and then match it up against the reference and find out the locations of the locations where the mutations have happened. Now, this obviously is extremely tedious and time consuming on a normal classical computer or even a supercomputer if you consider that. But using quantum computer, it would very easily be able to help you locate the locations of mutation, and you would be able to, it would basically enable a faster drug discovery for the problem. How would it do that? In a very short, simple way, what it would most likely be doing is to increase the probability of the locations which actually have mutations, that is the desired locations, and the other locations which have no mutations have lower probability. And that's how it tries to enhance the probability of the desired location and then point it out to us. So yeah, apart from these, of course, there are many other applications in the fields of finance, agriculture, and even the pure sciences like chemistry, biology, physics, genomics, etc. So yes, so the thing is now, I have been ranting on about how wonderful and fast quantum computers are. Now, the next question you might have is, how are they so fast? So, of course, these concepts would definitely be covered to you in much, much detail in the following sessions, but I thought I should be touching base on them as well. So I have a simple chart which compares classical and quantum computing. I'm sure you know about this, but let me just cover this. Yes. For the classical computer, you generally have bits to store information. And if you consider one bit, it can store either of the value of 0 or 1 at any given point of time. And in quantum computing, the classical counterpart would be the qubit that we use. And one qubit, in fact, can be in both positions 0 and 1 at the same time. This is what is called the principle of superposition, which I will be explaining soon. Now, this might not sound very significant to you, but think about extending this to multiple bits and qubits. So if you have two bits, it can be in one of the four possible states, right? 0, 0, 0, 1, 1, 0, and 1, 1. But if you take two qubits, it can in fact be present in all the four states at any given point of time with a certain probability that I have here. So the probabilities would be the C00, C01 values that you see. And with these probabilities, both the qubits would be existing in all the four states. So now you extend it to n bits and n qubits. N qubits would in fact have two power n states. Superpose is basically that the qubits are present in all the 2 power n states with certain probability assigned to each of those states. And this really is helpful in parallelizing computations and quantum computing. It would then be able to work on multiple solutions at the same time, which a classical computer cannot do. It has to perform sequentially because it cannot exist in all the states at the same time. But then I should also point out that there are certain tasks which are well suited for quantum computing, like the optimization tasks. You have a huge set of solutions, maybe million or 10 million possible set of solutions, and you want to find the best possible solution out of it. In such situations, quantum computing is definitely much, much faster than classical computing. Even if you want to find all solutions for a given problem, quantum computing works very well. Like I have given the example of the chess and how Deep Blue defeated the chess champion. It tried to identify the best move out of a set of possible moves. But then daily usage of computers, like streaming a video or talking to someone or using social media, for these kind of applications, definitely classical computing is much better. Classical computers are much better than quantum computers, at least at this point of time. And another, I think, a caveat for quantum computers is that they need to be placed in controlled environments, because here we are talking about quantum particles like electrons and photons, which are so small and minuscule. And again, you have to then, to excite them to the next energy level, you have to give that exact precise energy. And then you would be learning later in the course that a qubit can take complex positions as well, which means it's not just a spin, it's not just 0 and 1, but somewhere between this. I don't know if my mouse is able to, you're able to see my mouse, but it can be between 0 and 1 as well. And all those would be complex states, which require phase as well. So when it's moving from 0 to 1, it's called a spin. And then you have a spin shift and a phase shift. So adding all of these really makes the system very fragile. You have to literally apply that exact amount of energy and then keep it at that energy at that level for some time. So all of these really need a very controlled environment with very low temperatures, which is not so with classical computers, right? You can take your laptop, go anywhere you want. So yes, this is probably something that researchers might be working on as well. So yes. So now coming on to a little bit more detail on what I've discussed previously, that is the principle of superposition. This before starting off as to what exactly it is, I just want to explain um, the experiment, the thought experiment that went behind it. So I'm sure you all know about Schrodinger, the famous scientist, and he did this experiment with a cat. He placed a cat inside a box and closed it. And he asked the question whether the cat is alive or dead. Now, until you open the box, you wouldn't know whether the cat is alive or dead. So until you have not opened the box, the cat is basically in both the states, dead and alive. So you connect this to the concept of qubit. The qubit, until you observe the qubit or until you measure the qubit is in both states, 0 and 1. And then if you open the box, then you would know whether the cat is actually dead or alive. Then at that time, it would not be both dead and alive. It would be either dead or alive. So in a similar way, if you measure or look at the qubit, it would then fall down to one of the basis states, 0 or 1, if you consider the basis to be 0 and 1. So this is basically the concept of superposition, where you have, like I explained, you have a qubit being at multiple states, all the possible states basically at once. And if you take multiple qubits, a superposition of all the possible states would be what the qubits would be in when they are in superposition. And I'm sure you would go through how to use the IBM quantum Q and QSKIT to generate superpositions between qubits and all. And this, of course, like I explained, also improves the speed, because it is now able to process in 2 power n states. It would be able to process 2 power n solutions at once. And another concept that is that along with superposition is the reason why we see such an enormous speed benefit with quantum computing, and that is entanglement. So it basically says that if 2 qubits are entangled or strongly correlated with each other, then any change in one qubit would result in a similar change in the second qubit. And if you know the state of one qubit, you would be able to predict with 100% accuracy the state of the second qubit. And they don't have to be close to each other. They can be completely far apart. One entangled qubit could be on Earth and the other could be thrown away on Mars. And still you would be able to predict accurately the state in the other qubit if you change the qubit on the Earth. For example, if one qubit is with spin up, that is in the 0 state, the other would be spin down, that is in 1 state. And this really helps in improving the speed as well, because if you double the quantum bits, the qubits, it doesn't mean the number of operations or processes double as well, because now if some of these qubits are entangled, it would mean that when you know the state of one qubit, you would know the states of the other entangled bits as well, and you don't have to look at them. So yes, the basic principles guiding quantum particles, the superposition, entanglement, are the ones, the guiding principles to improving the kind of speed that we see in quantum computing versus classical computers. So all this while, this is my take on quantum computing and what the kind of applications that I like, and I have been using quantum computing and what I feel about it. So coming to my journey, so it in fact began a few years back when I was working with IBM, and I was supposed to do a stretch project in my team. And my then team lead, who I think had quite a futuristic vision, suggested that I look at IBM Q and quantum computing. Until then, I had zilch knowledge about quantum computing. And as far as I know at that time, although IBM was doing groundbreaking research in the field of Q computers, not many people in the lab really knew about it. So it was wonderful to actually do some courses. It was more of a study project where I tried to figure out where this really can be applied and what are the basics and basic algorithms. I remember doing a course on EDX as well in quantum computing, which is very useful. And I ended up also giving a poster presentation on quantum computing and IBM-Q at an internal conference in IBM as well. And yes, my journey still continues. So I've had quite a long break in between, but I have resumed my learning again. And last year, I also attended the Quantum Global Summer School using QSKIT Summer School last year, and which I would also be discussing about as well. And yes, I would really encourage you all to share your knowledge and experience. Please don't think that, oh, I don't know so much as to write a blog or something. I need to know more. Don't worry. Whatever you have learned, whatever you've read, please try to share with others, and that's how you improve your visibility in this field. Because like Dr. Chris said, there's quite a lack of experienced and knowledgeable people in this field, and it's really wonderful to share whatever you've learned with others. And this is my last slide, I guess. So just want to explain how my experience went with the IBM Global Summer School last year. I attended it for a couple of weeks, and it is taught by experts in this field from IBM research labs, and definitely no comments on them, and they are wonderful. They're extremely knowledgeable in their field, and you get to learn quantum computing right from scratch. I mean, right from the qubit level to advanced algorithms. They teach very well and very well structured program. You do have access to the IBM Q computers and other QSKIT textbook and other relevant material. But of course, all of this is still available online for you for free. But definitely here you have an added thing called guidance. Wherever you're struck, you know where to go, and you have the volunteers from IBM or the lecturers or even your peers who can help you with it. And of course, there are assignments as well. There are practicals as well, not just theory. So you have theoretical lectures, and then later you have lab exercises where they explain you how to use IBM-Q, and then you're given assignments and homework to work upon and explore what you have learned. And there's always some or the other messaging service like Discord or Slack where you can meet other people who have similar interests. And most important, I felt, was the quality of peers, because most of the times we feel, I mean, the kind of students that you learn is also important. And I have met so many people who were doing their PhD in quantum mechanics, quantum physics, and they wanted to understand how to apply and use IBM-Q and quantum computing for their applications. So I got to talk to them and learn a lot from them. So definitely you have peers who have similar interests and are as enthusiastic as you. And you have different country-specific groups as well. So it's really important with time zones, because you're working in your time zone, and other countries would be doing, I mean, sleeping or whatever. So it's good to have students in the same time zone as you, so that you can work together and can respond to you quickly. And of course, this is again a wonderful forum. You get to collaborate, interact, and network with people, because now that you're just starting your journey, it's all the more important to talk to people who share your interests, and who knows, you might be able to work with someone who has similar interests and wants to work on something that you like as well, and you both can collaborate and come up with a research paper or something. So yes, all in all, it was a wonderful experience, and I would probably attend it again if they chose a different topic next time. It would be wonderful to learn from the summer schools. And yes, I hope this is now clear. This is just joke on superposition. And also, I would like to suggest, if you guys have time, please read this book called In Search of Schrodinger's Cat by John Gribben. it's a wonderful book which gives you a brief on how quantum physics really started, right from Planck's black body radiation to double slit experiment till the recent advancements in quantum physics, which really give you that context that you need on how this whole thing evolved. And also has some interesting theories by Einstein about having the possibility of parallel universe as well. So yes, and of course, these are some references I have, and there are a lot of things to look forward to. IBM, I think, is planning to come up with a 433 qubit computer sometime this year, and also 1100 plus qubit quantum computer sometime next year to 2023. So just imagine, it's 2 power 1100 states possible solutions that it can come up with or optimize. So yes, we are in for some really exciting times, and yes, I wish you all the best in your quantum journey. Yeah.
Thank you. Thank you very much, Bhavana. A wonderful presentation. Really good, actually. I think suddenly, a lot of students, faculties, and the other developers who are part of this call, the workshop, certainly will get benefited on this introduction. The Chris at a very high level, and and you are at a level like where people can observe, and try to implement things. That's what I'd like to see going forward. And thanks for sharing your journey as well. And that's very good. And also thank you. I know that it's early morning for you, and you woke up early. I made you to wake up early and joining the call. Thank you very much. Really appreciate it.
Thank you. It was wonderful.
Yeah. Any questions for Bhavana team? Oh, this is like a chain of things people putting the I mean, do you see that, Bhavana, like a Q&A?
So the first question is not something that I'm sure, because I do not come from the field of chemistry, so I would not be able to help with that. Okay, what kind of courses you NPTL, I have not really looked at NPTL because I've always been tied with IBM all this while. So IBM last year had, so every year it comes up with a new topic on quantum computing. So last year it had given a summer school on quantum machine learning that I attended. And the year before that was the basics on quantum computing. But I forgot to mention an important point here, that you don't have to really attend the summer school to get access to all the videos. All the summer school videos, lectures, and everything, all the data is available on YouTube. I think I should have posted a link to it, to the YouTube channel, but maybe I'll just find it out and send it to you, Ganesh, and maybe you can forward it.
Yeah,
but
sure.
If you search on YouTube, you would be able to find it.
Yeah, sure. Certainly, I can pass on that to them. Sure. And on the chemistry side, chemical structures mostly confirmed through NMR, IR, and even by crystal structures, etc. Right? How the quantum computing helps on this regard. Certainly, we will answer that, in next few sessions. Definitely there are some experts, will add, some insights on that as part of this.
Yes. Okay. So regarding the second question, there is an NPTL program. The IIT Madras, they are conducting, a professor is in charge, and she completed the PhD in the IBM lab, quantum lab, and now she is giving a 4-week course on the quantum computing from the NPTL. I think this may be the second question, and there is a lot of courses also taking place in quantum, and I think NPTL they are doing well, and I think I seen a course, a 4 weeks course. It's organized by a professor from the, I think she belongs to a chemistry department. She did a PhD at the IBM, especially in the quantum.
That's good, sir. There are a lot of courses, even MIT, yes. Berkeley, a lot of people are offering, but from our point of view, there will be some kind of the connected talks and connected things,
Sure.
we are going to have, as part of the app, whatever we are going to set it up. And also like, some kind of access to quantum too, I'm planning. Let's see how it goes. But, I do know that, the IIT Madras and IIT Delhi recently announced, a quantum course by Monica Agarwal. Like that, many people, coming out with, some plans and all the stuff. This is all good. But, we are also like, going to give some kind of a specific things which are going to be very helpful for the students who are attending as part of this workshop.
Yes, sir. I think we request all the participants, please give your feedback. The link is shared in the chat. I think participants, so that we can consolidate and we can giving a certificate for the entire 3 days. We'll consolidate the entire attendance and we'll give the certificate for all the participants. You just fill the feedback, you give a feedback so that it will be very useful for our organizers. Okay,
Sure.
sir. Thank you.
So
Sure.
there's a question here, which I would probably attempt, Ganesh.
Yeah, please go ahead. Go ahead.
So someone has asked, what's the difference between quantum computing and HPC? So as far as I understand, like even Dr. Chris pointed out, they are completely different phenomena. I mean, they're based on entirely different concepts. So HPC normally is used. I mean, it uses supercomputers or GPUs to basically parallelize computing. It uses a system or a cluster of computers to parallelize and improve the performance. But quantum computing is, I mean, of course, even there, you basically use supercomputers which have a central processing unit running at a certain clock speed. While the basic difference lies there, that quantum computing is entirely different. If you'd have seen pictures of how a quantum computer looks, it's really, really different from the normal computers that we look at. And it's based on the basic quantum phenomena that happens in the atoms, in the electrons and photons. And apart from that, quantum computing is really good for certain applications, like I mentioned. And you with just few qubits, even if you take 2 power 53, 53 qubits, you would have 2 power 53 states, and 2 power 53 is a really, really huge number. You cannot have I mean, the optimization problems that you have if you compare the performance of quantum computers and a supercomputer. You literally can't have 2 power 253 clusters of computers looking at your data. So that's where you have the quantum advantage, quantum supremacy. I don't know if I have answered the question properly. This is my take on it.
Yeah, and also like, the applications, whatever HPC is trying to solve, we can also solve it using quantum computer. And what the report says, there are a lot of reports already talking about how this quantum computing will replace all the HPC data center. 76% of HPC data centers worldwide plan to use quantum computer by 2023. See, it looks like it's very, I don't know, it's possible or not. And it's a report, it's a like ATOS and IQM kind of, teams, putting together. 71% plan to move on to on-premise quantum computing by 2026. So that's going to be a good race for a lot of people, can create opportunities on this.
True.
So those who want to, run HPC data centers, they can use quantum kind of computers, to solve the problems too. But there will be a lot of porting work, optimization, but there will be a lot of porting work will be there. Good. Thanks, Bhavana, for pointing that out.
Thank you.
Any other questions before we go to the conclusion of the session?
Yes, sir. We'll conclude, sir.
Okay. Again, I thank Bhavana for the wonderful presentation. Thank you again. I look forward to work with you more, Bhavana. Thank you.
Thank you.
And
Thank you.
sir,
And
sir,
Dr. Shivagami, madam.
yeah,
Important.
please. Yeah.
Thank you, sir.
Thank you, sir, and thank you, ma'am, for the fantabulous session. Not but not the least, I welcome Shivagami ma'am to deliver the vote of thanks.
Greetings to all of you. It's a great privilege and joy for me to extend a vote of thanks to all those who have contributed in one way or the other to make this workshop a success. So first of all, I would like to thank from the bottom of my heart our chairperson, Tirumadi K. Dhanalakshmi Ammal, Pro-Chairman, Rotarian MPHF RSK Raghuram, and Principal Dr. D. Vasudevan for being the catalyst that stimulated us to do our best and standing as pillars of strength. I also thank our professor and head, Dr. A. Vincent Anthony Kumar, for organizing this international workshop on quantum computing and applications. I also thank our chief guest, Mr. Ganesan Narayanasamy, and the speakers of today's session, Dr. Christopher Coleman and Ms. Bhavana, for sharing their knowledge with us. We understand that you have taken time out of your very important schedules to contribute to this workshop. Thank you for your valuable contribution. Last but not least, I would like to thank our staff members, participants, student volunteers, and well-wishers who made this workshop a grand success. Thank you, one and all. Thank you.
Thank you. And let's all catch up tomorrow morning at 10 o'clock Indian Time, Standard Time. Thank you
Yes,
all.
sir.
Thank you, sir.
Thank you very much.
Thank you.
Thank you, ma'am. Finally, I thank our chief guest for the wonderful session. And this session may bloom our students into a beautiful butterfly from a cocoon of hardships and struggles passing in the way. Thank you all for spending your spare time with us. Thank you.
Thank you. We will meet tomorrow by 10 o'clock.
Thank you.
Thank you, sir.
Bye.